this part of thermodynamics, we're going to start talking about ideal gases. It's going to seem a lot like chemistry. And an ideal gas is a gas in which molecules don't interact with each other. So I'm going to do a T-chart over here. We're going to put real gases on this side and ideal on this side. Okay? Now, in a real gas, the molecules attract each other. But in an ideal gas, there is no attraction between the molecules. The collisions in a real gas are not elastic. There's going to be some sticking between them because they're attracting each other. And here the collisions are perfectly elastic. Which means no kinetic energy is lost in the collision. And they bounce off of each other like little hard billiard balls or something like that. Now, you should remember this from chemistry, relationships between pressure, temperature, and volume. And if you think of pressure as being how hard the molecules are bouncing off the walls of the container, temperature is how fast they're moving, and volume is how big it is, you can easily figure these out. So for the first one, let's say we're going to increase the pressure. Okay? Then we're squeezing it, it's going to make the volume go down. Now that's assuming constant temperature. All right. And then if I was to graph this, we would have P versus V would make a curve like this. Because one goes up, the other one goes down, they're inverses. Now, as temperature goes up, okay, the molecules are going to be moving around faster, and if my volume's constant, they can't spread out, so they end up hitting the walls harder since they're moving faster. So the pressure would go up. Now again, that's assuming constant V, and that would look like this. As temperature goes up, pressure goes up, like that. And then the third one, as temperature goes up. Okay, now if the container can change size, the molecules are going to move faster, they're going to spread out, it's going to make the volume go up. This is assuming constant pressure. And that would look like this, temperature versus volume, and it would go up like that as well. Now you don't have to memorize which one's Boyle's law, which one's Charles' law. In fact, I never remember, but you do need to know what's going to happen. Now, the ideal gas law we're going to use is this: PV equals nRT. Okay, P is pressure in pascals. That's the unit for pressure. And 1 atmosphere is 1 times 10 to the 5th pascals. So you may have to convert. A lot of times I'll give the pressure in atmospheres, and you have to know that it needs to be in pascals. Volume is volume in meters cubed. A meter cubed is a very big volume, so you'll probably have small numbers for that. N is the number of moles. R is a constant. It's 8.31 in the units we're using. And then T is temp in Kelvin. Now you remember in the stuff we did earlier was, for instance, Q equals MC delta T. And for the delta T, it doesn't really matter if you convert it to Kelvin or not. You can do it in Kelvin or in Celsius. But when you have a T by itself like this, not a delta T, your temperature has to be in Kelvin. Remember, to get the Kelvin temperature, it's equal to Celsius temperature plus 273. Now, this can also be if n is constant. You could rewrite this as P1 V1 over T1 equals P2 V2 over T2. Sometimes this is a little bit quicker. Now, here's an example. We have a sample of oxygen with 20 moles at a temperature of 20 degrees Celsius and a pressure of 1 atmosphere. We want to know the volume of the gas. So I'm going to use this equation, PV equals nRT. I have to remember that I need to convert. So 20 degrees Celsius plus 273 is 293 Kelvin. And then pressure of 1 atmosphere. Remember, 1 atmosphere is 1 times 10 to the 5th pascals. Now I'm going to rearrange this. If I want to get the V by itself and trying to find the volume, I would divide by the pressure. So V is nRT over P. So N is 20 because we have 20 moles. R is 8.31. And T we just found was 293. And then we're going to divide that by the pressure of 1 times 10 to the 5th pascals. And we'll get a value of 0.49 meters cubed. So that was part A. Part B, now we're going to change the temperature and change the pressure and find out what the new volume is going to be. I'll plug in the same equation. So the number of moles stayed the same, so it'd be 20. R is 8.31. The temperature now, if it's 80 plus 273, that's going to give me 353 Kelvin. And my pressure is now 2 atmospheres. That's going to be 2 times 10 to the 5th pascals. And when I do that, I get a volume of 0.29 meters cubed. We have one more example at the top of the next page. Right. In this case, we have a sample of gas at temperature 40 degrees Celsius. Remember, we got to convert that, so that's going to be 313 Kelvin. Volume of 1 liter. What will be its volume if the temperature is raised to 100? So we got to convert that too. That's going to be 373 Kelvin. And constant pressure. So when you have something like this, we're changing from one temperature to another temperature. I could use the PV equals nRT, find the number of moles, then use it again. But it's actually going to be a little quicker just to do it this way. Okay, PV over T equals PV over T. Now, it says a constant pressure. If the pressure is constant, I can cancel it and not worry about it. Okay, so now I have a volume of 1 liter over, the temperature was 313 there, equals the volume I'm looking for over 373. When I solve this, I'll end up with a volume of 1.19 liters. So I didn't convert the liters, I left it in liters. Just remember, if I have liters on this side of the equation, I'm going to end up with liters on the other side. And this makes sense. The temperature went up a little bit. If the temperature goes up a little bit, the volume should go up a little bit.